Hello and welcome to the UK column. Tonight we are joined by David Siegel, who has been on the programme before, of course. And since the last time David was on the programme, we have run a climate course which lasted 12 weeks. And two of the participants of that course were Joe Walton and Liz Avramides. Welcome to the programme all. First of all, David, maybe we could start with you. And how was the course for you? This was the first time you've attempted to run this type of course, and you had a very diverse audience. So how did it go from your point of view?
Well, first, there are actually 3 students here because you showed up for most of the classes.
That's true.
And you attempted to make sense of all this stuff. So that's a big effort for a busy guy. And I think we had about 55 students, almost all from the UK, although some from Canada and one from Costa Rica. And I think 1 or 2 in the United States. And it's a pretty complex topic. I think the one thing everybody learned was that it's more complex than you think, much more. And there are many, many levels, and there's as deep as you want to go. And I think most people in the class wanted kind of the first couple of inches, but not the next 100 feet, which I presented. And it's a lot of physics. So one of the interesting things that came out of the class, and I'm interested to hear from the other students, is that it was just interesting overall because you learned a bunch of physics and a bit of chemistry, although I'm not as up on my chemistry, but we learned a lot of physics and a lot of kind of interesting stuff along the way. So it wasn't just climate, and we didn't really focus on the politics. We focused on the science. That's what a lot of people are missing. And so I invited a couple of students. They're kind of ringers. They got it. They spent time on it. They dove down the rabbit hole with us. And so I wanted to ask you guys, how did you see it between kind of interesting physics or interesting science versus really learning about the climate versus you're there because you want to be armed with facts and arguments so you can tell other people who don't believe, who believe otherwise. So Liz, how would you summarize it?
I would say it was learning about the science. I had no idea how complex it all was and how necessary it was to understand physics in order to really form any sort of opinion. I think as a chemist, I found that I thought I understood at least some of the basic principles of climate change, and then I realized in the end that I understood very little, that it's vastly more complex and that it requires a lot of studying in order to get to the bottom.
Listen,
I don't know if anybody got to the bottom ever.
Well, indeed.
No, probably not.
But Liz, I got the impression from the course that you had a bit of a head start on the rest of us because of your chemistry background. How necessary do you think it is to have some kind of scientific background if we're going to get grips with this stuff?
I think it helps enormously, but I don't think that should be a deterrent. My particular take on it put me in a good position to understand the radiative theories and the radiative model of climate change, and therefore to understand that isn't really as cut and dried as I'd been led to believe. So that helped me, but I think everybody can get something out of it as long as they're prepared to put a bit of effort into it.
I think there were 3 levels, Mike. The people who were just completely overwhelmed, who watched the videos several times and kind of retained almost nothing, just because they probably shouldn't have been in the class. They're nice people, interested, but it was just too deep for them. Then there were the science people. That was probably another third, and they were pretty interested and like they got something out of every class and had good conversations. And then there are kind of the people in the middle who were interested for sure, spent a bunch of time, got overwhelmed a lot, but still what they've told me is that it really increased their confidence in being able to talk with other people about. They don't remember 99% of the content, but it increased their confidence in being able to talk to people who were saying things that were obviously nonsense. Joe, how would you?
So for me, I came in with a non-science background, but I read a lot of stuff and feel like I can, if I study, I can get there. So sometimes halfway through a class, I'll just be like, I just need to check what that actually is because I don't know what it is. But if you just do those little adjustments, I don't think it was too bad. I think it was well paced because you started off with a nice big picture, the 4.6 billion years, and immediately the scales taken right out. So that's a great starting point, because I think a lot of the time people who read the news are very focused on the kind of what's happening now. It's really hot now, and but yeah, great to start off with that, kind of looking at things on a bigger scale, and then looking at the universe, the celestial mechanics side of it. I thought it was really interesting. Like you said, the physics, and I think every week I'd sort of feel like, oh, yeah, I'm sort of getting there now, and then we'd kind of reset with the next episode, because it's like there's a huge other piece that you have to know to just, figure out the puzzle. So for me, the water and the air movements were tougher to get my head around. I felt I got a really good understanding of the greenhouse effect and more of the physics type stuff, the radiative models and things like that. Whereas I probably need to study again more the El Niños and the oceans and the air currents, which I'll probably enjoy from doing a course again.
Can I ask you both, how much time outside of the course did you put into it while the course was running?
I was reading and watching mainly. I did read a bit of the book, but it was quite dense. So yeah, I think I started reading the book, that one, yeah. But I think I probably would need some more scientific and statistical study to kind of read that more fluidly. But I was spending a few hours every week watching videos, and like Tom Nelson's podcast was a great center, and we were sharing a lot of material on the community, and that I enjoyed that as well. So I'd just be at work at lunchtime, I'd just kind of, instead of reading the news, I'd be like chatting about photons or something. And that was quite nice, just being a community doing something a little bit different.
Mike, what did you get out of it as a student?
I got a lot out of it as a student. I basically knew very little about, as Joe says, how many billion years were we talking about? 4.5 billion years or so. I had no real understanding of how the climate has developed over that period of time. Also, although I had some awareness, shall we say, off to the side here somewhere, that galactic and universal impact on the climate on this planet is important to take into account as well. I didn't understand how that worked, and so there were a few eye openers along the way. For example, the whole business of the effect of traveling through the spiral arms of the galaxy, and it made my understanding of celestial mechanics there completely failed, because I didn't even know that the solar system traveled through the spiral arms of the galaxy, and so on. So lots to open my eyes on. But as well as that, I would take your point about it just giving, whether I retained or whatever percentage of it I retained, which probably isn't a huge amount, to be quite honest, because it's going to require a lot of ongoing effort to internalize that stuff. But I would say it has certainly given me confidence to know when I'm being sold a pop. Let's put it that way. And although I may not be able to make an educated argument in all cases, I certainly will be much better prepared when somebody is telling me something which simply is not correct.
Good. Liz, anything?
Yeah, I put quite a lot of effort into it. Not every day, but as I had the time available. More of the effort I put in was to do with what I already knew, so trying to understand in more depth so that I could judge to what extent I felt I'd been misled by the simplicity of what's been presented. So yeah, I think the more effort you put in, the more you'll get out of the course. And some of the concepts were completely new to me, so they would require quite a lot of study, I think.
I want to let people know this is an advanced climate science class. You should have at least 20 hours of independent study. That would be the minimum in climate science. It goes pretty deep, and this book is, I would say, graduate level material, not undergraduate. And so if for people who have a bit of science background and enough time or interest to try to make up those gaps in their knowledge, it's pretty fascinating territory to explore.
David, I've got a question for you because we went through the climate course, and part of that was the greenhouse effect. Now, just recently, and we'll put the link to this in the show notes for this program, but just recently you've been back on Tom Nelson's YouTube channel with an update to your view of the greenhouse effect. And so maybe you could just explain a little bit about why that update is necessary.
Oh, I've even learned so much since then because people gave good comments. And one of the great things for my education in climate science is that GPT has gotten better in the last couple of months at talking with me. It's just less full of garbage now. And so I can have real conversations about things, and it'll give me equations and we can solve them. It's been pretty good. So I even have an update on that, and I'm going to give that today. I have an updated talk today on the greenhouse effect as I see it now, which I think is even, there's more to it than what I gave with Tom. And it's really just complex. There's a lot going on, and there certainly is a greenhouse effect. And that's what I want to show in the presentation today. There is a greenhouse effect. How much of a greenhouse effect is there, and how much does it affect climate? And the short answer is that Javier Vinos calls the CO2 greenhouse effect the pilot light of the planet. It's been helping warm the planet, especially make overnight temperatures less cold since the planet was formed, because the planet was formed with plenty of CO2, enough CO2 that the first 100 parts per million have always been here. And that's all you need to have that higher overnight temperature effect. After that, it's saturated, and I want to explain that because I came up with a new concept for that. And more CO2 doesn't do anything. So CO2, the up and down of CO2 over the last 4 billion years hasn't made a difference at all. But there is a huge water vapor greenhouse effect. And I've understood that a lot better now too. So that's what I want to talk a bit about in my presentation today. This will be really kind of the first core class we're giving away for free here. So everybody gets kind of a whole overview of the class. And then the actual class will be 10 weeks starting on September 11th, diving into all of these areas and unpacking these two models, try to get it right. I'm always, as Liz knows very well, coming back to class next week saying, oh, I screwed this up. I got that wrong here. Let me correct you. So always trying to be just less wrong all the time, get information from other sources. We had 3 guests last time. They were fascinating. So try to put the whole thing together, by putting first together this overview and then filling in all the gaps. I just want to mention quickly, it's going to start September 11th at 7 p.m. UK time. There will be another class for people in North America on September 12th at 6 p.m. Eastern. And this class you guys have already had. It's the cognitive tests. So there are 2 cognitive tests that help you calibrate your critical thinking skills. And as we all can maybe, how do you feel about the test? Were the tests valuable? What did you learn? Don't give away the test, but what did you learn about yourself in the tests?
I learned I know nothing, but Liz.
Yeah, it was fascinating. The test was fascinating. Yeah. So it really makes you think about what your assumptions are, and sort of try to think about why you're doing something or why you're believing in something. And it's useful, yeah.
Joe, I think you did fairly well in the tests.
I think I did really well in the first round, but then sort of progressively worse as, as I went through. But yeah, it was good. It did make you think, like, why am I setting my limits so wide? It's almost like a kind of arrogant thing. It's like I could actually just make this easier for myself, by being less biased, which I thought was.
And these are tests that have nothing to do with climate. These are basically epistemology, how you think about facts, how you deal with information from the real world. And we will start talking about climate in the second one, when the class really begins. So this is just a first session to help people calibrate their thinking. It's free, and Joe and Mike will put in the show notes the links to the two classes. September 11th at 7 p.m. UK time, also 2 p.m. 2 p.m. Eastern here. And then September 18th for people in North America at 6 p.m. Eastern. And those are free 2-hour webinars to help you kind of understand how you think about the world. And you should bring a lined pad of paper and a pencil or pen. And then the class starts a week later on the 18th and 19th of September, and it will go 10 sessions. And all the sessions are pre-recorded. All the lectures are pre-recorded, so you can go through them at your own pace. And then we'll have a live question and answer and discussion and present some topical presentations every week at Wednesday, 7 p.m. UK time, and Thursdays at 6 p.m. US Eastern time in the US. If the sun is the size of a basketball, how far away is the Earth and how big is the Earth?
That was you're giving away one of the questions. So that was one of the questions. You'll have to omit that one, perhaps.
No, that wasn't. That was actually in the first day. That wasn't from the tests. See, already we don't know how much we don't know.
That's correct. Do you remember the answer to that, Joe?
If the sun is the size of a basketball, how big is the Earth?
It's probably going to be, so I can describe it, like maybe about 4 millimeters across or something, size of a...
Wasn't it a sesame seed or something?
Yeah, something like that. I can't
about 1.5 millimeters, smaller than a peppercorn. And how far away is it from the basketball?
Yeah, totally gone on that one. So I'll just say 3 meters.
No. It's gonna be miles. It's gonna But I can't remember how far. No, you're gonna have to tell us, Liz. No, we've all forgotten.
I don't remember.
100 feet.
Oh.
So think about a peppercorn that is 100 feet away from a basketball. That's the relationship between the sun and the Earth. So there's a lot of little cute things to know like that'll kind of, help keep you sharp and thinking about the world, but also it all tends to come together when we understand how heat moves from the tropics to the poles, and that's what is going to be in my presentation next.
David, the other thing that sort of struck me running through the first course was that this is still a moving target. So although there's a lot understood, and there's a lot that we can say that demonstrates that the official climate change narrative, there are lots of questions to be asked about that, and lots of skepticism to be had around that. And there's a lot of science that they're ignoring when they present their reports and so on. Still, the science is not settled.
No, not at all. There's much more to learn, especially about the past and the future. The past, it's easy to cherry pick your data. So as we say in climate science, the problem with climate science is that the future is known with so much certainty and the past is so impossible to figure out. And the future models are just all based on computer models that all practically share almost all the same code and the same assumptions and are tuned for the same reasons. And there are a lot of political motivations to get all this, to have it go a certain way. And so, first of all, there's a lot of noise. And second, we really are starting to understand how the climate system actually works. And I would say that this this is the leading book on how it actually works. Now, if that's what you want to understand from a science point of view, my class is going to be very appropriate. If you want to understand how all the tricks are played in the political agenda by various groups, that's Tom covers a lot of that. I've given a previous talk about that, but that's not what the class is about. And further to your point, Mike, the future, many experts and the people I talk with, there are many different views on how the next couple of hundred or 1,000 years plays out. But then after, say, 1,000 years or so, everybody's pretty much in agreement that the Milankovitch cycles will take over again.
And if anybody wants to know what those are, they're going to have to sign up to the course.
That's right.
Excellent. Right. Well, look, David, would you like to give us...
And I've got my handy-dandy Milankovitch tool, which everybody recognizes because we spend so many hours with this thing. And so that... and me moving various tennis balls and ping pong balls and things around to show the relationships between the planets and the moon and the sun. So yeah, I will excuse Joe and Liz if they want to. There's no, you're there in the community. These are my helpers there in the community. You'll see them if you join the class, and you can ask them, whether I'm full of it and need correction, or if you have any questions about anything, they're there wanting to help, and we're all learning all the time, all of us. So with that, thank you, Joe and Liz. You're welcome to stay or not, but it will be about a 50-minute presentation now. Okay?
Right.
Okay. Well, look,
Thanks.
thank you, Joe and Liz, and if we'll see you again soon, no doubt.
All right, here's my updated framework for understanding climate. I gave this talk to Tom Nelson in late August. We're recording this now at the very end of August. And I've got here two of my best students, Mike and Liz. And this is going to be about a 50-minute overview of my framework for understanding climate. The more you study the climate system, the more complex you realize it is. I've spent a lot of time recently re-understanding the greenhouse effect, and I've realized that most of my previous videos weren't scientifically accurate. So in this presentation, I want to try to put the climate conversation in perspective. I'm always trying to be less wrong, not more right, which is a little refreshing in climate science. So if anybody sees something I should correct, just put some comments and leave sources under this video, and I'll be happy to go explore those more. So we will start with the two ways that I think are appropriate to think about climate science. All right, the radiative model and the thermal model. This is a quick summary. The radiative model looks at the energy balance between incoming shortwave radiation absorbed by the Earth and the long-wave infrared radiation leaving. This is a popular but inaccurate model of the climate system. In the real world, energy coming in gets converted to heat, and that heat gets transported not just back up to space, but via 4 important gradients that we will explore, and I've shown 3 of them here. So let's start at the beginning. At the sun's core, you two will know this question, 2 hydrogen atoms fuse into a helium atom, creating a huge amount of energy in the form of plasma, gamma rays, and high-energy photons. Once a photon is generated at the core, how long do you think it takes, on average, to make its way, moving at the speed of light, to the surface of the sun? Who remembers that? Anybody? Mike?
Liz?
Liz?
I think it was 1,000 and something years.
No.
No, wait a minute, a million.
I filled your
It's
head
a
with
really
so many
long time.
factoids that it's all scrambled, which
It's a
is
really long time.
completely understandable. Mike, how long does it take?
I can't remember, David. I'm very, very sorry. My brain is not functioning today. But
150,000 years.
yes.
150,000 years for a photon going from the core to the outer rim of the sun, where it can then speed off into the cosmos. All right. And that begins its journey into the solar system and beyond. 8 minutes later, some of those photons, a small number, arrive on Earth. About 170 petawatts of solar energy arrives to Earth at all times. About 30% of the photons that should hit the surface are scattered by clouds, land, and water, and they go back to space. That's the albedo. What happens to those that hit the surface? Well, we're going to look at this two different ways. The radiative model is first, starting with the greenhouse effect. So the radiative model, and we've all seen this diagram, uses the energy balance diagram to show how greenhouse molecules like carbon dioxide and water re-radiate heat back down and heat the surface. They go up, then they come down, they get re-radiated, and they go round in circles, and that heats the surface. According to this model, radiation is the primary way energy goes from the surface to the top of the atmosphere, while convection and evaporation are small compared to radiation. The thick red bar on the right shows radiation coming back down to the ground from the atmosphere. This is called back radiation, which we'll learn more about. And they claim mostly that is from CO2 and also from water vapor. And methane, of course, which is now the new evil gas. CO2 is a critical gas for life on our planet. I want you to have appreciation for this. Even though there's only 4 in 10,000 molecules of CO2, it's everywhere around us. All of us are almost certainly sitting on or within a few meters of some carbon-based material right now. What is around you that's in your living room or in your office made of CO2? Well, you are wood, limestone, concrete. So if you're anywhere near concrete, that's all just limestone. Plants, paper, food, animals, all of it comes from the tiny amount of CO2 in our atmosphere. So now I want to tell the story of the greenhouse effect. To start, a high energy photon comes from the sun after its 8-minute journey and strikes the Earth. It hits something, and that high energy photon is annihilated and heats whatever it hit, which then radiates long wave photons out according to the temperature of the thing, the sand, the rock, the pavement, whatever. One shortwave photon generates about 20 long-wave photons, and so they have much less energy. So let's follow one long-wave photon as it goes up. First, if the outgoing photon happens to be in the right wavelength of 10 to 14 microns, then it leaves to space unimpeded. This is called the atmospheric window. And Liz, I have huge news about the atmospheric window. I completely understand it now, and we're going to go over it in one of the live classes. It's very exciting because it was always a bit of a mystery to me, but I've figured it out. And so that's about 12% of the photons go straight to space. Second, as we know now, the photon can't hit an air molecule like nitrogen or oxygen and transfer its energy to the air molecule. That's impossible. These atmospheric molecules are transparent to infrared radiation. The photon can only interact with greenhouse molecules. So when the photon encounters a greenhouse gas molecule, and I'll just use carbon dioxide as an example, this molecule absorbs the photon and begins to vibrate at a higher energy state. By the way, this is not a quantum phenomenon. This is a long-wave photon adding whatever energy it has to the molecule's energy. Now, two possible things can happen. In the first possibility, that vibrating CO2 molecule could hit an air molecule and transfer its energy mechanically versus via collision. So the air molecule speeds up, increasing the air temperature. And this is like a billiard ball hitting another billiard ball. The first ball comes to rest and transfers all its energy to the other ball. This mechanical transfer is called thermalization because the vibrational energy turns into velocity. And as we learned in a previous class, velocity is temperature. In the second possibility, the CO2 molecule re-radiates a new long-wave photon out in some random direction and then goes back to its previous energy state. This is the radiative model. Greenhouse gas molecules are constantly absorbing and re-radiating long-wave photons. So the energy makes a random walk up through the atmosphere and eventually ends up at the top, where it's finally emitted and goes to space. This is just radiation, though. it doesn't change the air temperature at all. As those higher energy greenhouse gas molecules encounter air molecules, they transfer energy mechanically, thermalizing the energy, increasing the air temperature. The long wave photon coming in from the bottom encounters a greenhouse gas molecule like CO2 that raises the molecule's energy state, as we just saw. But it takes on average about half a second before it de-energizes and re-radiates a photon out in a random direction. Long before that half a second is up, the CO2 molecule is struck by an air molecule and transfers its energy mechanically, heating the air. Thermalization is far more common than re-radiation. It could be on the order of millions or billions to one, because air molecules are constantly bouncing off each other billions of times per second. So the collision almost always happens first, increasing the speed of the air molecules. That warmer air then rises by convection. And watch Liz, in case I make any mistakes. You just raise your hand and call me on it. But I think I got the number. I think I got the words right. So you got a mistake already?
Well, it's just carbon dioxide is a linear molecule.
What?
And also carbon dioxide is a linear molecule.
Yeah, but it can bend.
It can bend, yeah. It does bend. That's the energy.
All right. So when it's normally in its normal resting state, it's linear.
Yeah.
So we'll go back to the collision almost always happens first, but feel free to raise your hand. It's fine. Increasing the speed of the air molecules. The warmer air rises by convection. At the top of the atmosphere, there are far fewer air molecules and actually fewer and fewer water molecules, water vapor. So at some point, an air molecule bumps into a greenhouse gas molecule that finally emits a photon to space. And this is how 100% of the energy arriving on Earth eventually leaves to space, through dethermalization via a greenhouse gas molecule at the top of the atmosphere. CO2 does a huge amount of work ejecting thermal energy out to space. Okay, I have to make my CO2 molecules straight. I'll do that. But CO2 is a well-mixed gas, and it's all through the water column. And they are always emitting long-wave photons all the time at the temperature of wherever that air parcel is. So some of these photons get radiated back down to the surface and start over, and that's the actual greenhouse effect. But the Earth's surface is predominantly water, so let's understand what happens in the oceans. Wherever there's a lake or an ocean, some incoming photons hit a water molecule on the surface and evaporate it, sending it up into the air. From there, the moist air expands and rises as convection moves the expanding air upward. As it gets higher and colder, water vapor then condenses into droplets that form clouds, and that releases energy, which is then dethermalized by a CO2 or water molecule and later sent to space. There's no CO2 required at the beginning of this whole chain. It's just sunlight evaporating water from the surface. Here's the picture in the oceans. About 10% of sunlight hitting the oceans reflects back to space. That's the albedo. 20% are vaporized on the surface and rises into the atmosphere, as I just said. And then about 50% of the photons penetrate down tens of meters into the ocean, the top layers. And then about 20% more makes their way deeper into the deeper ocean layers for transport around the world. So about 70% of that incoming energy heats the ocean water directly. And not even that is true, Liz. There's actually a lot of fascinating details there. We'll come back to ocean heating in a minute. We're now ready to answer an important question for the atmosphere. How much energy is transported by mechanical vibration and how much by radiation? Some people claim the radiation dominates. Others claim it's almost nothing. So rather than using theories and diagrams, I want to look at downwelling thermal radiation using real-world data from the Ceres satellites. It's different in different places. We'll start with the North Pole. The poles are generally under clear skies. In July, the Ceres satellite instruments measure about 200 watts per meter of downwelling long-wave radiation going to the Arctic surface. During those months, the North Pole receives sunlight all the time. So the atmosphere there has a mix of water vapor and CO2. And we know there's an inversion at that time too. They both produce downwelling, both CO2 and water vapor produce downwelling radiation. But during the darkness of January, there's still 100 watts per square meter of greenhouse effect. At that time, the air is extremely dry. So most of this is done by CO2, but not all. So think of it this way, though. If you look around at night on the North Pole with thermal imaging goggles and you look up at the sky anywhere, you're not going to see black. You're going to see light because the goggles turn downwelling infrared radiation into light. And from this, we can see that during the summer, about 120 watts per square meter is coming from water vapor down and another 80 watts per square meter from CO2. We're going to encounter those numbers again. In Antarctica during summer in January, we're seeing the inversion and the sunshine. Also during January, warm air is coming in from the tropics, and that mechanical energy sends more radiation down to the surface. Antarctica is the driest place on Earth, so most of this radiation is from CO2, but not all. Why is the greenhouse effect lower in Antarctica than in the Arctic? Because Antarctica is that much colder and higher. Average elevation in Antarctica is about 8,200 feet. So there's less atmosphere and it's a bit colder than the Arctic. At sea levels, these numbers would be higher. Now going to the Sahara Desert, skies are usually clear and there's almost no water vapor. So CO2 is responsible for the overnight temperatures in the desert. At night in the Sahara, it's cold, but the air is much warmer than at the poles. And it's much less cold than it would be otherwise. And that's why the numbers here are higher than we saw for the poles. I'm not going to translate watts per square meter into degrees because that's where all the fudging is. And you can have your way with those numbers and get any answer you want. There are too many factors to do that. But here we see quite a lot of downwelling radiation at night, even under clear skies. Much of this is from CO2. In the rainforest, there's a smaller difference between day and night because water vapor is doing most of the work. And the water vapor is there all the time. During the day, evaporation pumps most of the energy into clouds and up to the top of the atmosphere to escape. At night, the greenhouse effect is huge, mostly because of water vapor. And this is under clear skies. So now let's add clouds. Clouds reflect light away from Earth. They reflect heat down. They insulate, and they have their own internal radiative activity, not to mention electrical charges. I'm only showing nighttime data because that shows the greenhouse effect by itself. With clouds, there's more energy being re-radiated down to the surface, and this is why cloudy nights are generally warmer than clear nights. With clouds, water vapor does the vast majority of the work, while CO2 is probably around the same low level we see in the desert and at the poles. So let's look at the water that gets vaporized into the atmosphere. These are nighttime figures over the oceans. These are nighttime figures for downwelling infrared radiation, the greenhouse effect, to the ocean surfaces. It depends on temperature, air pressure, and moisture. But CO2 likely doesn't contribute much to this greenhouse effect. Water vapor can do all the work here because water vapor and CO2 cover the same wavelengths, which we remember from another class. And since we know downwelling radiation can't penetrate the oceans, no amount of CO2 can heat the oceans. So let's just kind of summarize this. The oceans determine our climate, and the oceans, both warm and cold, have something like 330 watts per square meter of long-wave reflected radiation coming down to the surface. That is the greenhouse effect. But how much is CO2 and how much is water vapor? Over most of the ocean, there's a lot of water vapor. But at the North Pole in darkness, there's hardly any. So I would say that most of this 100 watts per square meter, maybe 80 watts, is a CO2 greenhouse effect. That would be down here. So on average, I think worldwide at sea level, about 80 watts per square meter of greenhouse effect from CO2 really does exist. CO2 constantly, this is the crux. This is kind of the crux slide right here. CO2 constantly feeds energy into the air column. It can absorb and transfer energy mechanically to the atmosphere millions, maybe even billions of times per second, while emitting a photon every half second or so. So in my view, I'm going to introduce a slightly different way to say it. I would say CO2 is actually unsaturated, or we could say it's always below its capacity to warm the air. The same amount of CO2 can feed more energy into the air column if more energy comes in from the sun. More CO2 won't help feed more energy into the system because it only takes a handful of CO2 molecules to do the job. Plus, in most cases, water vapor is doing the same job, so CO2 is only necessary where it's very dry. Javier Vinos calls this the pilot light of the climate system. It's been happening for billions of years since there's always been at least 50 parts per million of CO2 in the atmosphere. Now, Will Happer, just to unconfuse people if I possibly can, says CO2 is saturated, which is why it has reached diminishing returns. And there's a technical meaning he uses. It's very precise. So I'm using the word differently. And so perhaps we could say CO2's ability to re-radiate is saturated, but its ability to pump mechanical heat into the atmosphere is unsaturated. It's, for all practical purposes, it's unlimited. So I believe CO2 can continue thermalizing arbitrary amounts of long-wave radiation because it has a huge capacity to do so. And perhaps we could say CO2's ability to re-radiate is saturated, but its ability to pump energy into the atmosphere is unsaturated. Is that kind of clear? I'm trying because it's a difficult technical, and I'm trying to kind of change the meaning of a word here. I'm basically meaning that water vapor does the lion's share of the work to heat the atmosphere, and no, a bit more CO2 won't heat the air enough, regardless of how much sun comes in, because it always has the capacity to thermalize those photons. By the way, when we talk about watts per square meter, we have to keep in mind this is long wave, not short wave radiation. You can't compare long wave watts per square meter with short wave incoming sunlight watts per square meter, because long wave photons can't penetrate the oceans. And this is a common mistake. These numbers aren't comparable. So that's the radiative model, and we'll actually go more into these details in the class. And Liz and I will have some really interesting conversations about how all these things works, because it's absolutely complex and fascinating. But I want to move on now to the thermal model. This is how the Earth's actual climate system actually works. And to do that, we need to focus on heat, not radiation. So I have another presentation that I've made with Mike on heat versus temperature. And that's the one with the water in the oven, remember? But it's important to realize that long wave radiation is not heat. Temperature is the speed at which atoms and molecules are moving. Heat is the number of atoms or molecules moving at the same speed. One molecule zipping through space can be very hot but have almost no heat. 2 kilos of hot iron has twice the heat of 1 kilo of iron at the same temperature. So photons don't have any heat, even if they're in the infrared, because photons aren't atoms. Atoms jiggling, the speed of atoms is heat. Now, this is interesting. This is an infrared photograph. You can't see the heat directly. You can see the infrared photons everything gives off. Infrared photons transport energy, not heat. So there's no heat until these photons transfer their energy into molecules, until they thermalize molecules or atoms and increase their speed. That's how you feel heat from a fire. Did I screw that up, Liz? I think I might have gotten that right. Heat always moves from hot to cold, and that's what drives our Earth's climate system. So we'll understand that using 4 gradients, 3 of which are here. There's a mystery gradient coming up in a few minutes. The first gradient is the vertical lapse rate. Almost all the heat in the atmosphere is down here in the troposphere at the bottom, the first 10 kilometers that we're familiar with. Most photons escape to space below the tropopause here, as we have just seen. And there's a whole section on the vertical lapse rate in the course. The next gradient is the rotational gradient from day to night and back. The sun's energy comes from a single place, but it's distributed over a sphere, yet the radiation to space goes out at all angles. So remember that the greenhouse effect takes place in seconds from the bottom to top. So if you just look at radiation, you'd say the Earth is hottest at noon and coldest all night long when there's no incoming radiation. This is where we can really make good use of this concept of radiative versus thermal model. Because what actually happens is the surface and the air are hottest around 5 p.m., 6 p.m. at the end of the day. We don't experience peak temperature at the time of peak radiation because the atmosphere and pressure systems build up heat during the afternoon and don't release it until after the sun begins to set. This is driven by collisions far more than it is by absorption and re-radiation. During an inversion or heat dome event, the radiation doesn't change, but the pressure does, and that changes the surface temperature significantly. This shows that the radiative model isn't very helpful and the thermal model is a better match. So now let's look at the meridional temperature gradient, which is the change in temperature from the tropics to the poles. We spent weeks on this, right, students? and that's what the book is about, and there's a lot to it. So I'll summarize. We define the tropics generally as 30 degrees north to 30 degrees south, and the temperate zones from 30 to 60 degrees. The tropics cover half the surface area of the Earth, but this area absorbs 2/3 of the energy coming in from the sun. This is because outside the tropics, the angle of the sun is spread over a larger distance, and the sun's energy has to come through more atmosphere. The oceans absorb about 60 petawatts of energy at all times and transport about 11 petawatts away from the tropics to the poles where it escapes from the poles. It's about 20% of the energy coming in to the tropics. So now if we widen this area to 40 degrees, we have a net energy surplus from 40 degrees south to 40 degrees north. So more energy enters these latitudes than leaves to space. This is a surplus. And that water that gets heated first goes west because the Earth is spinning east. And when it hits land, like right here, it turns toward the poles. You can see it at the eastern point of South America. And of course, it happens on the eastern edge of Asia. And this sends more, the shape of this, because the equator is here, the shape of this will send more water to the North Pole, more heat to the North Pole than to the South Pole. But not by a whole lot. And this is just one feature of many that influences heat transport and invalidates the radiative model. From 40 to 60 degrees, the temperate zones, the surface and atmosphere are roughly in equilibrium. And this is where most of the weather is. The warm water interacts with cooler air and causes storms, hurricanes, and chaotic air movement that carries heat from the tropics to the polar regions. So heat is being transported via storms toward the poles. And beyond 60 degrees, more heat escapes the system than enters. The heat is transported to the poles about 2/3 via air currents here in the temperate zone, and about 1/3 through the ocean currents. When ice melts during the summer, and this is one of the interesting things we learned in the class, it's the climate system storing heat like a battery. When the polar summer ends, that heat is released as ice forms, and that heat goes up through the polar vortex, completing the circuit from incoming at the equator, up and around, to out through the poles and up to space. And I want to drive this home. It takes a lot of energy to melt ice. Each summer, starting in March, when ice melts in the Arctic all summer long, that is not a heat wave. It's not weather. That's the Earth's way of storing energy so it can get rid of that energy in the following winter. When the water freezes 6 months later, it's all released. Well, a lot of it gets released, which then goes up through the low pressure zone in the polar vortex to space via long wave photons that get dethermalized. The energy gets dethermalized at the top of the polar vortex. More melting ice does not mean more radiation. It doesn't mean the Arctic is melting. It means more heat will be released the following winter. So about 20% of the excess of the energy coming into the oceans gets transported away from the tropics and escapes through the polar vortices. Along the way, it converts between heat and infrared energy many times as it follows the temperature gradient from warm to cold and out to space. So far, so good, I hope. Now, these gradients drive the Earth's climate, and here's how we visualize them. The temperature of the equator is in the center, and the South Pole on the left, North Pole on the right. The planet is turned 90 degrees to match. During the Cretaceous, 100 million years ago, the temperature gradient was pretty flat. Most of the Earth was very warm. The continents were concentrated near the equator, and there were very few storms. It wasn't as easy to move heat to the poles, so this Earth is very hot and very humid. Here's snowball Earth, which probably happened 750 million or 440 million years ago, although there's still uncertainty about that. It would have been caused by a combination of low eccentricity, the arrangement of the continents, and feedbacks. At its coldest, the temperature at the equator might have been below freezing at the equator, and there may have been some solid CO2 at the poles, also called dry ice, because the poles were much colder than today. The distance from the Earth to the sun, along with the shapes of the continents, gives us the meridional temperature gradient we have now. And this is this blue line here. So we're in an ice age because we have ice at the poles year round. The shape of this curve determines the Earth's climate. This diagram from Javier Vinos's book shows the energy distribution by latitude. The light blue dotted line represents the incoming energy from the sun, with the equator in the center and the South Pole to the left, North Pole to the right. Now notice the blocking of sunlight here at the equator due to clouds. That's this little dip. And there's a heat surplus inside of 40 degrees, as shown by the red area. So I'm taking the previous concept and just putting data into it, and a net loss of heat at the poles, shown by the blue shaded areas. This data shows that the radiative model is invalid, and the climate system moves quite a bit of heat from the tropics to the poles. This is not much mentioned in the IPCC documents. So now I'll build a simple but realistic energy budget. About 29% of incoming energy is reflected off clouds and land and water back to space. That's the albedo. About 3% is absorbed by ozone in the stratosphere. 20% is absorbed by the atmosphere itself. That leaves 48% going to the surface. About 17% of that energy is absorbed by the land, and it makes its way back out to space via convection, conduction, and radiation, as we have seen. About 31%, twice as much energy, goes into the oceans, and about half of that energy, actually more, 70% of that energy, a small amount, about 20% of that energy evaporates water and goes up, and the other, about 80%, penetrates and heats the water, and that heat gets transported poleward. So there's one final temperature gradient I haven't shown, and that's the thermocline going down into the oceans. The thermocline is largely driven by salinity, since the saltier water is, the heavier it gets. In the North Atlantic Ocean, the formation of ice sends tons of salty water down, hundreds of thousands of millions of tons, I don't know, lots of salty water down to the bottom of the ocean to return back through along a kind of a belt at the bottom of the Atlantic Ocean and Pacific. Did you know that all sea ice is essentially fresh water? Salt water doesn't like to freeze. So because of this sinking water that's more salty, the Earth can be out of radiative balance as excess heat can go down into the oceans and stay there for hundreds of years. And it can come back out over decades or centuries as the gradients allow. It's part of the global ocean conveyor belt, which connects 4 of the world's 5 oceans in a current that's driven by temperature and salinity. It takes a given water parcel about 1,000 years to complete its journey around the Earth. So sunlight can go into the ocean, and that heat can stay in the ocean for hundreds and hundreds of years before finally coming back out and going to space. You don't see that in the radiative model, but you do see it if you study pressure systems, ocean currents, and oscillations. So here's an important slide from Javier Vinos, and this is just a summary of what we talk about in the class. It shows detrended data, which is just the relative ups and downs. At the top is the Atlantic multi-decadal oscillation, a 65-year cycle that's going to turn negative in about 5 or 6 years. In the middle is the Pacific decadal oscillation, and look, it has a very strong correlation to temperature. This tells us that oscillations play a very important role in our climate system. So here's an assembly of most of the main temperature series that try to show how CO2 is driving temperature with this hockey stick shape. But even here, the fit with the AMO and PDO graphs is better than with CO2. You can see the temperature is going up, then down, and this matters. Anything over about 30 years counts as climate change, and then back up again, down again. This corresponds much more to the solar cycles and ocean cycles than it does to CO2. It's even more pronounced if you remove the urban weather stations that are heated by humans. Here, the blue dashed line shows data from rural stations that haven't been compromised. The blue line shows the very cold years that occurred about 3 years after the Krakatoa volcano erupted in 1883. Despite the volcano, rural stations generally show warmer, and then it equalized, warmer temperatures in the past and milder temperatures in the last few decades, which is the opposite of the red graphs you see on social media now. That's because CO2 is not the driver. On the order of hundreds and thousands of years, temperature trends are mostly driven by sunspot cycles, which drive more or less energy into the oceans. There's a 2,500-year cycle called the Bray cycle, and another 1,000-year cycle called the Eddy cycle. And you see how they both were at their minimum 400 years ago, and that caused the Little Ice Age? And 2 more times before, sunspots are quite sunspot series are quite regular. And these cold periods put an end to several flourishing civilizations. The end of the Bronze Age was particularly brutal. We can predict from this that the next double low point will be around 2450, when it may again be possible to ice skate on the Thames River, no matter how much CO2 is in the atmosphere then. So to sum this up, and I've talked about this up in the class a lot, we have 2 main drivers of climate at all timescales: momentum and chaos. And this transcends all the timescales. Momentum drives the orbits of the planets around the sun. It almost certainly drives sunspots in some way. Momentum drives the continents into different configurations, which drives ocean currents into their oscillations. We can predict certain cycles better than others. There's plenty of variability both within the cycles and from one cycle to the next. Almost nothing repeats perfectly because there are too many things in motion and they all influence each other. On the other hand, we also have chaotic mixing and stochastic events that can't be predicted and can be catastrophic or very surprising. For example, when 2 or more cyclic events happen, the result is a chaotic phenomenon like the Maunder minimum. Many phenomena are in a buildup and release cycle, like earthquakes. Something has to reach a certain threshold to trigger a release. And this creates lightning strikes, El Niños, earthquakes, sudden stratospheric warming, volcanoes, and much more. So there are also things in the chaotic domain we don't understand, like cloud formation and precipitation. Some of these are quasi-cyclic and many are simply unpredictable. All right, so I'm going to summarize. In the radiative model, greenhouse gas molecules are necessary to heat the air, and the more of them there are, the more air they heat. In the thermal model, greenhouse gases are necessary to heat the air, but CO2 is already working to convert energy to heat and heat back to energy, and it has plenty of capacity to do so. More CO2 has no effect on temperature because we already have the minimum amount needed, which is around 100 parts per million. On the other hand, more water vapor does contribute to overnight temperatures, but is dwarfed by the thermal effects during the day. So now we're going to ask 8 inconvenient questions for people who use the radiative model to explain how their model is the right one. We've been over all these in the class, so let's see if we can remember some of these. The first one is, why is the Earth's temperature highest in July when the Earth's overall temperature is highest in July when the Earth is farthest from the sun by about 3 million miles, and it's coldest in January when the Earth is closest to the sun? A radiative model can't explain this, but a thermal model can, because the northern hemisphere has far more land to heat up as the heat moves from the tropics to the North Pole, while the southern hemisphere has far more water, which absorbs heat and sends it directly to the South Pole. Land has a much larger influence on surface temperatures than oceans do. And that's where we measure surface temperatures. When we talk about the temperature of the Earth, it's almost always land temperature. Next question. Could something else be causing the warming of the last few decades? Doubling CO2 would have a tiny effect on temperature, if any. But that's not true for clouds. Even a 1% reduction of cloud cover would have a significant temperature effect on temperature. More clouds increase reflection and reduce temperatures. Fewer clouds mean more direct sunlight hits the Earth, creating higher temperatures. Over the past 20 years, clouds have decreased, so more energy has entered the system. And we see a corresponding amount of energy leaving the Earth's atmosphere, which shows that the heat isn't being trapped. There's just more energy coming in from the sun. So the question is, what could possibly explain more heat escaping to space? The radiative model predicts that outgoing long-wave radiation will remain the same as heat builds up in the climate system from a buildup of more CO2, because the sun doesn't change in the radiative model, but CO2 does. But the thermal model accurately predicts more heat escaping to space as more heat enters, though with various time lags for heat transport. Question number 4, what caused the spike in temperature in the last year or so? Was there a rush of increased CO2 that even the models didn't predict? Or was it several factors working together? Decreased albedo, positive phase of the AMO, a couple El Niños, the peak of solar cycle 25, which we're just ending now, which we're just about at the peak of right now, actually. A change in ship fuel type last year, which put fewer aerosols into the air, and a huge underwater volcano eruption. The volcano, the Hunga Tonga volcano, added 140 megatons of water vapor to the stratosphere, has increased the greenhouse effect in the stratosphere, and has caused a lot of surface warming by radiating downwelling long-wave radiation down to the surface. But it'll dissipate over the next 5 to 10 years. It might be radiative, but it certainly isn't man-made, and it certainly isn't climate. And Liz, I know much more about how that happens now, so we'll discuss it in the class. All right, question 5, what is heating the oceans? The Argo floats started measuring mid-level ocean temperatures 1,800 meters under the surface in 2004, and the result is about 0.04 degree per decade in less than 2 decades. Back radiation from CO2 can't warm the oceans. In fact, if anything, downwelling infrared radiation actually cools the oceans a bit through evaporation. The only thing that explains this rise in ocean heat is more direct sunlight penetrating the water. Fewer clouds, not more CO2, would do that. 6, why isn't Antarctica heating? What's up with Antarctica? It's not obeying the rules. Antarctica is the driest place on Earth. CO2 has risen there, the same as everywhere else. You can see it in the background here. No change on that, and it's a well-mixed gas around the world. And yet temperatures on the Antarctic plateau are not moving with CO2. This is the coldest weather station on Earth on the East Antarctic plateau. Here's the actual South Pole station where the researchers are. They recorded their lowest ever surface temperature in 2021. No hockey stick shape here. This year, Antarctica had a sudden stratospheric warming event. It had happened a few months ago. The last one was in 2002. Those events have been happening for millions of years. They're rare, but like their more counterparts that we've studied in the Arctic, they are part of the natural cycle moving heat to the poles. That's because CO2 doesn't cause any warming at the poles. I want to stay on this for a second. 2016 paper in Nature Climate Change, which is the official dogma of the Church of Climate, shows proxy and satellite temperature data for Antarctica going back 200 years. And I want to read you their conclusion in the paper. Climate model simulations that include anthropogenic forcing are not compatible with the observed trends. This suggests that natural variability overwhelms the forced response in the observations. Yes, the IPCC does not cite that particular paper in their literature. And look at the tropics. Why aren't temperatures in the tropics increasing? This is Pamban, India. From a thermal point of view, stable tropical temperatures make sense because it's covered by clouds and water vapor to the same degree all year round. If albedo is going down, you'd expect a slight rise over the last 20 years ago or so, and that's exactly what we see, a slight rise in temperature. Papua New Guinea. From a radiative point of view, we should see a hockey stick shape here, but the tropics are insensitive to changes in CO2. Seychelles, Mahi Island, this is interesting, has data since 1890. And look, you can see about a 1 degree rise since 1980. That's from a remote weather station that they moved to the airport when they built it in 1972, so the weather people could more easily record temperatures near their offices. So this story is of stable temperatures followed by the growth of their tourism industry. This isn't a thermal model. This is data manipulation model, which is also very popular. Here's a hockey stick shape showing sea level rise in the American Samoa Island, where the UN Secretary General Antonio Guterres last week made a video saying sea level is rising fast. He went to American Samoa specifically because there was an earthquake in 2009, and since then the island has been sinking at a rate of 6 inches every 10 years. And Guterres said, for the cameras, this problem that we see in Samoa will not stay in Samoa. It will be happening more and more everywhere in all coastal areas. So I'm guessing that means CO2 is going to be causing a lot more earthquakes in the coastal areas around the world. If you only have the radiative model, it looks like CO2 drives our climate. So here's a question. Look, if water vapor is the main greenhouse gas, why doesn't the IPCC say we just should reduce water vapor? Why aren't there billions of dollars available for entrepreneurs to suck water out of the atmosphere? Well, the answer to that is it's not about climate, and it never was. I'm going to leave the questions here, but there are many more. So now let's talk about the future. If you use a radiative model, then the Earth is going to cook over the next 200 years because there's no way humans are going to reduce their CO2 emissions. This graph is from Javier's book. Shows about 120 years in the past and 180 in the future. The IPCC prediction is this jagged red line produced there by their models, which are programmed to be sensitive to CO2. And this is the new 4.5 prediction because the previous 8.5 prediction wasn't selling very well. So they shifted. Now we know CO2 will continue going up until nuclear power becomes mainstream and it will take hundreds of years to go back down. So the radiative people are sounding the alarm and selling solutions that undermine privacy, security, and the economy in exchange for authoritarian control over the weather. If you use a thermal model, you understand that solar variation drives our climate via the oceans. The black line is Javier's prediction. And on this timescale, he believes solar cycles, these are the sunspot cycles, will be the main driver of temperature. He thinks temperature will continue to rise for another 50 years, and then it will start to descend after the Eddy solar cycle peaks. Here's the Eddy 1,000-year solar cycle peaks later this century, and then start to descend back down. My prediction is a little different, shown in red here. I think that it won't quite be as hot as Javier predicts. I think the AMO and the PDO will have the biggest influence. So the next AMO negative cycle, which starts just in about 5 or 6 years, will bring temperatures down or flat for about 35 years. We'll have a little rest from all the alarming Guardian articles. And then the radiative alarmists will have 3 decades of new records, heat waves, and fundraising. It'll be fantastic. Then there'll be a drop in solar radiation around years 2100 and 2200 from the Feynman cycle. You see this Feynman cycle? That's a cycle of cycles, which you can see. And you know who the Feynman cycles are named after, don't you? Mike, Liz?
Richard.
Joan Feynman.
Oh, right, okay.
Richard Feynman, who was a solar scientist. And this cycle of cycles is named after him. So at the end of every century, roughly, temperatures come back down. That's why we had the pause before, 20 years ago. And we'll have more pauses in the future as we have lower sunspot activity. All right, so I believe ocean oscillations will continue to dominate, but the solar cycles are a big input to the ocean oscillations. So it's all based on solar variation, which the IPCC does not acknowledge. And these are, of course, just educated guesses. It'll turn out differently in reality. But we can look forward to more plant growth for the rest of the century because of increased CO2. Look at that. Look at how green it's going to get in the next 50 years. Fantastic. Longer term. And we had a class on this, so this is a refresher. We will again have ice sheets coming down and covering most of North America and Europe. Although in 20,000 years, I don't know if North America and Europe are going to be called North America and Europe. But 20,000 years ago, it was very cold. And 20,000 years from now, it will be very cold. Starting in about 1,500 years or so, temperatures, and I think maybe closer to 1,000, temperatures will start to descend and the ice sheets will start marching down over the northern parts of the continents, while obliquity will be high enough in 35,000 years to start a new interglacial like we're in now. But eccentricity at that time will still be too low for a strong one. But if you go out 80,000 years, both obliquity and eccentricity will combine to make a really nice, comfortable, warm, great vacations interglacial climate, a bit warmer than what we have today. And so the lesson is buy your beachfront property when it's still underwater about 70,000 years from now, and then just wait, and a few thousand years later, you'll be glad you did. So I've talked about 2 mental models for understanding climate, and it turns out you need both, the radiative and the thermal model, because they always work together. It depends on temperature, moisture, and air pressure, but there's always been about at least 50 parts per million of CO2 to keep the surface at sea level about 80 watts per meter warmer than it would be without the CO2. And we need to study heat transport via temperature gradients, since they drive the rest of our climate. And for that learning, I turn to 2 people who've helped me the most. Andy May, whose books and blogs are a great example of unbiased critical thinking. Many of us who are trying to figure these things out are flexible because many of our assumptions are wrong, and there's still a lot we don't know. The IPCC is frozen in their views and will do anything to drive their political agenda. and Javier Vinos, who has taught me so much, and I'm glad to help others learn from him. This first book is difficult, but is good for people who want the big picture without all the details. The one on the right that we use for the class is really a master's degree level climate science. So the class begins on September 11th at 7 p.m. in the UK. That's with the tests. And Thursday the 12th at 6 p.m. And then again, the actual class begins on September 18th and 19th. And you can register for all these classes at climatecurious.com. Did I screw it up too bad?
You did not.
But any general questions? Or it's been for your viewers, it's been over an hour. So if anybody's still here watching, we'll get maybe the last words from Mike.
Well, David, I'm just going to say thank you very much. And thank you, Liz, and also Joe for being here. Joe had to go, unfortunately, but thank you, Liz, for being here.
Thank you for inviting.
The other thing that we should say about this, David, is that anybody that did the previous course is going to be allowed to join for this one as well. So I have no doubt in my mind that there are going to be lots and lots of questions from people that have already completed the first attempt, and I'm going to be very interested to see how the second go at it improves the situation for us all, because I think it probably is going to take several attempts to get to the bottom of it. The one question that I had was, you said on a number of occasions, and you said that on the climate course that we did as well, that once you get to above 100 parts per million CO2, that anything above that doesn't really make any difference. I don't want to go into any detail on this right now because we need to end, but maybe you could just sort of summarize why that is.
Sure. And this is hard, but I wanted to try to put it into my presentation that CO2 can take incoming long wave radiation coming off the ground and thermalize it, right? But it can do that almost forever. It is not saturated in that regard. It can why? Because it only emits a photon every half a second, and billions of times a second it's available to just absorb and then get struck by a molecule and transfer its energy like a billiard ball to that molecule. So let's say at sea level on a hot day, I don't know, somewhere, it's like a couple billion to 1 ratio. And CO2 can do more. All it has to do is get hit by a molecule and it just transfers its energy. So it's not really that, it's not full. You know, it's pumped, its capacity, CO2's capacity to pump heat into the atmosphere is practically unlimited. And we need it for the first 50 or 100 parts per million or so to do that, because there are places where there isn't enough water vapor. And it's been doing it for 4 billion years. And if you add more energy coming in through, say, more sunlight, hits more asphalt or whatever, and then turns into thermal, infrared photons, those photons can easily get thermalized by the CO2 that we have. And adding more CO2 does not increase. Think of it as a capacity thing. It has tremendous capacity to continue to thermalize that energy, and more CO2 won't do anything. Won't change the capacity. It's hard. I probably need better words.
No,
a good analogy or something.
Yes, I mean, I get what you're saying, but it is hard. It is hard.
It is.
Yeah. That's why
it's also hard because we've been trained to believe that more CO2 produces more heat. And that's just simply not true. More CO2 won't do more incoming energy produces more heat. That's why the Earth has been warming since 300 years ago in the Little Ice Age, and it will continue to warm next century or so, because we're going to be getting more energy in from the sun.
From the sun, yeah.
Yeah,
And
it's not really building up; it's leaving the system as it comes in. So there's no tipping points, and there's nothing scary, and the Atlantic decadal oscillation is not about to shut down. There is no shutdown. It's going to be business as usual and a little warmer over the next couple hundred years.
And who can complain about that at the best time? So, okay, well, look, David, Liz, thank you very much, and Joe as well. We will end it there for now, and let's see how this course goes. And I just would recommend anybody that has any interest in this sign up, because it was a lot of fun the first time. I'm quite sure it's going to be more fun this time. So thank you very much, both.
Thank you.